scheduling. So, how about if we let's schedule things right now? I am not here Friday. My understanding, I'm probably coming back either late Saturday night or late Sunday night. Monday, I have a 4A review from 10 to 1. So the question is, I gotta do one to two more lectures. Okay? I think once you see me do AC circuits with phasors, you know everything already. What you don't know is how to handle the math. And that's my job, is to teach you the math. So note that we're not doing anything new. It's just a mathematics thing that we got to do. So so if you look at our schedule, it's Wednesday and Friday. So we have a final that we're supposed to have from 7 to 10 a.m. And then Friday, I moved the final because, by the way, this is not something new. I always have to have the final on that day. And in fact, it was every Friday until 2 years ago when they did a whole rescheduling of the college. And they started putting it on Wednesday, and I said, oh, hell no, you gotta put it on Friday. So Friday is our final exam. What time should we start?
7. I was like 7.
7.
6.
I can't get you at 6.
What time are we ending?
If I remember from the last several years, like, I'm using the exact same final exam that I've used forever. And if you do that right, that final exam is about 2 hours for the majority of the people. I'm not trying to beat you up. All I'm trying to do is sort of like keep you in check at the very end. I think the circuits you've seen already, maybe modified a little bit. And so my experience is that if you already know what to do, it just goes. It's really fast. There are some people at 3 hours, but I am not trying to make this like, it's not like a regular exam. I treat it much less. So it sounds to me like you can do 7 to 10 a.m. So this is what I'd like to do. I want to do a lecture here on Wednesday. And I don't think I can talk for 3 hours just because I've been talking already. So I'd say we should shoot for 2. So if that's the case here, we have this room for this time, so I think we should meet at 8 to 9:50. Okay? So we should lecture at 8 to 9:50. And one of the things that we should worry about here is that we probably need one more time. So if everything was perfect, I would have tried to lecture on Friday or Saturday so that the vast majority of people can come. And then we would do Wednesday, and that would be it. So I think we need one more. Okay? And I'm going to suggest Monday. I could do Thursday. Whatever. Does anybody care what time it is? As long as it's not conflicting with one of your finals. Yes.
Is that Wednesday the 22nd? Or, oh, sorry, never mind. Never mind. It's the 22nd.
I don't know the date. Yeah, so they promised me this semester it would go back to Friday, but apparently they didn't do that. So now they're telling me next semester it will be scheduled always for Friday. So the question is when to set another lecture. And what I really think here is that I think that this last lecture should be a review. What do I mean by a review? That means that we should go through all of the problems. Like, I'm going to ask you the simple circuits ones. I'm going to ask you, I believe, There's gonna be one noder mesh. There's gonna be a Thevenin. I don't even know if I'm gonna have you do a Thevenin. Because you have to do a Thevenin with an RC circuit already. So I may drop the Thevenin problem and then force you to do it on the RC circuit. One op-amp, a first order, a second order, and 2 Phasor questions. Okay, so I think it's somewhere between 6 to 7 problems. So you can see what I mean by being a 2-hour, final exam. And let me tell you, these circuits are not challenging at all. They are not challenging. I mean, I would never give them to you as a quiz. I would never give them to you on an exam. That's what I mean, but I'm expecting just to try to round everything up. That's what I want to do with this exam. Don't you think I've tested you enough? I don't need to do that again. So I need to set another lecture. So, yes.
We do Tuesday or Thursday?
Yeah.
Tuesday, I'm screwed.
Monday.
Because Tuesday, actually, I could do Tuesday, but it'd have to be later. Because I have a 7 a.m. final, I have a 10 a.m. final that ends at 1. Like we could meet at 2?
Yeah.
How about Tuesday, 2 to 4? So let's look at multiple times. So there's a remark here would be 2 to 4 p.m. What's another time that would work? Monday?
No.
If I did Monday, it would have to be around 2 to 4. Yeah. We could also do another Wednesday, like 2 to 4.
I just 2 lectures on Wednesday. I got final.
Okay. Okay, so how many Tuesdays?
10 to 1. Can you repeat the question?
How many people want a Tuesday lecture right here? Right now, that's by far the vast majority. That's probably 80% of the people. All we gotta do is we gotta find them. So what I suspect here is that Tuesday, we might do it in the lab. Or see if the engineering lab room downstairs. I doubt it if I'd be able to get this room. So I'll have to just check. So we're gonna have to play it by ear. Okay, so that means we'll walk in here. If nobody's here, we'll do it here. If not, we'll have to search. At the end, they'll be in the lab room. Okay? So then that means that the true final exam is this date right here. Right? This is the final exam. Now, let me tell you what's happened in the past. It didn't happen last semester. There's graduation on Friday. Who's walking Friday? Because I'm definitely, I go to graduation. So I'll be looking for your asses. Right? So, but this is what's happened for years. Right after the exam, I invite you to my house for a barbecue. Would that work for people? Or would it work better on Saturday?
Friday.
How many people would shoot for Friday? Okay? I mean, we're talking like, we get out of here at 10, I'm saying we start at noon. Right?
I'll do Friday.
Yes.
Can you bring anything or is it just?
Yeah, I'll give you a little slip. Okay, I'll give you a little slip. With the wrong address, of course. I've been doing this for a long, long time. 20 years ago, even my first semester here, I started doing this. Okay? So I've been doing it for a long time. Okay, so I think we're clear, right? We're doing Tuesday, we're doing Wednesday, we do this, and then then we do the barbecue afterwards. Do we have to be any more clear than that? Okay, let's get started. So, we are now in chapter. We're now talking about steady. So, here we go. We're talking about steady state analysis, so check it out. When you look at steady state analysis, what you're finding here is that you're getting some function here that has a natural response and has a forcing response. So if you remember, what does the natural response look like? If I look at this natural response, it can be complicated, but ultimately, what you'll find here is that you'll get something of this form right here. So note that if I have, like, any type of oscillation, a damping of any sort here, it's going to look something like this. So if I look at steady state implies kind of like T is what? 5 tau or 1. And what we do know here is that term just disappears. So that means we never care about the natural response. It's gone. The only thing that exists is the forcing response. And what we're going to find here is that our solutions here, it's customary not to write them in terms of sines, but in terms of cosines. And so what I mean by AC steady state, if I was to be a little bit more clear here, you're going to get something like this here. Okay? You're going to get something like this. So what I said here is that it's customary to rewrite this thing. Now it's a complicated process, not complicated like you can't do it, it's just a lot of mathematical jargon. And I don't feel like it's going to help us right now. So what we can do here is that we can rewrite these constants B1 and B2. We could force them into this form. And if you look at my solutions in my notes, I can rewrite this thing so that it reads now, let's say B cosine, where I'm going to get an omega plus some phi right here. So I could do trig identities. I could, mess around with this. And our goal here is to really look at this solution right here. And what we're going to do here is that we're going to do something like this here. What we're going to find here is that these functions are periodic. Okay, so these guys are periodic functions. Which implies here that this function has some period that allows it to be repeatable here. And so when we start to look at this AC jargon, I really got to only understand one thing about this, because it just keeps repeat about it. And so what we want to do here is that we want to go in and we essentially want to say, if I have this time domain solution, right? I call this guy a time domain solution. And that time domain solution turns out to be very, very difficult to keep doing when you go from a second order circuit to a third order circuit, or to a fourth order circuit, or fifth order circuit. And so what they do here is they use this technique, which are known as phasors, like we were talking about in lab. So what we find here is that the time domain solution is too challenging to apply when, how do you spell when? Okay, I got it. When circuits are higher than second order. Okay, the time domain solution is too challenging. Like, just think about it. If you had a third order equation, wow, that's nasty. That means you need 3 initial conditions just to get what? Let's say if I had 2 capacitors and an inductor, I'd have to get the initial conditions of those capacitors and the inductor, and then I got to get another 3 more solutions for the derivative of the inductor, for the derivative of the capacitor, the derivative of the other capacitor. It gets way more challenging. And so somehow we would have to do a system. But what we find here is that, as we said in lab, as stated in lab, phasors make these circuits linear. And when they make these circuits linear, this implies then that we can apply all DC techniques. That means I could use VDR again, CDR, node, mesh, Thevenin, anything that you would like. You know, resistor techniques. So everything comes back. The only challenge here is that we have to move into the complex plane, like we talked about in lab. So the challenge is doing calculations in the complex plane. Okay? We have to do that. So that being said here, let's go set it up here. Okay? So I'm assuming that you've had some complex analysis, that you've had some way of messing around with it. So this is a review, even though you may not have seen this. Okay? So we're going to do, so essentially a phasor is a complex vector that is exponential. So here we go. So if I start to look at this thing here, my whole goal is to tell you what do I mean by a phasor. And what we do here is that as we were talking about in lab, I get this J equal to the square root of -1. You know, I was talking to some math instructors and they were saying like, you know, this complex plane, none of this shit is real. And I'm going like, what do you mean? What do you mean? That's bullshit. This is a horrible. The person missed the boat. Just because we talk about an imaginary axis, it doesn't mean that you don't get real calculations. You do, right? God, the guy really missed the boat. So what we're seeing here is that we can let's define a complex number. And I'll define it as C as A plus JB. So this time we got to really get into the details. Okay? Then there's the complex conjugate. I'm only writing this so that you can learn the language if you don't know it. Complex conjugate means that I take C star, and that means here that I take all negative values, all imaginary values, and I give it a negative sign. So when I look at this guy here, what we break this into is that there's a real part of C, and that's A, and there's an imaginary part of C, which is B. So in this case, the imaginary part here of the complex conjugate would be negative B. And you're going to see that how we move from the time domain frame and into the complex plane, which is called the frequency domain, is this very simple process right here. Okay? This is where we're going to be in the complex plane, and then to move back, you're going to see that we're going to take the real part of the function. And so then we'll be able to sort of like pull out the details. And so what we want to do here is that when we multiply, so if we multiply vectors, okay, so if we multiply vectors, so the common thing here is to do C star C. So C star C is the same as the magnitude of C squared. And when you do that, you get what? You get A minus JB, you get A plus JB, and when you multiply this out, you get A squared plus B squared. So look at that. This imaginary number gave me a real number. And if we want to calculate the angle, we could do, the things that we were talking about in polar form here. But the one thing that you want to worry about here is that the imaginary J can never be in the denominator. Right? It can never be here. So if I look at C here, I can never have A and just leave the imaginary down here in the denominator. And what I mean by this here is that the way you get this thing out of the denominator, look what I had to do. I have to take its complex conjugate. So what do? I multiply by C star, which is the same as 1. And if I do that, I'm going to get A plus JB times A minus JB divided by A minus JB. And you can see here that this will then be A squared, B squared, A minus JB. And you're going to see that the reason why we always want this in the numerator is because we're going to be taking the polar form of this into our Phasor vector. Like I haven't defined a Phasor vector. And so what we then say here is that now in polar form, what we write here is we say that C is equal to A plus JB, and then I do what we do anytime we do in polar form. What do? I have to define a new R, which is what? The magnitude of this guy, and I need to define an angle theta. And so what you find here, where, right, R must be A squared plus B squared square root. In other words, C star C. I took the magnitude of it. And then the angle theta is then the tangent inverse over the imaginary over this guy here. So when I look at this vector right here, what I'm seeing here is that I'm seeing this form. I'm in the imaginary axis like this, and then I have a vector. So I have a point right here, and that point right there is A plus JB. Just to make sure that we're clear, if I project this down, that's going to be the point A. If I project this across the axis, that's going to be the point B. And then this vector, this polar vector, C, looks like this here, where I have this angle theta here. So what do they call a phasor? You're going to see here that ultimately this is what we call a phasor vector, right here. In polar form, you're going to see that there's a piece that's missing, but you're going to see that that piece always cancels. But that's what we call the phasor vector right there. So there's one super important form here. What we find here is that there's something called Euler's relation. You know, I don't know if I ever told you the story. When I was an undergraduate at the University of Arizona, I had a math professor that his hobby was going around the world to take pictures of headstones, right, in cemeteries of famous mathematicians. And he actually used to put them on his door. Like sometimes, you know, he would have multiple of them. You know, what a hobby. Yes. But what he did here is that when he went to Euler's grave, you know what it said? Euler. Didn't have to say anything else, right? This dude is something else right here. Right? He's one of the most prolific mathematicians of all time. So when you look at this relationship, EJ theta is the same as cosine of theta plus J sine of theta. You're going to use this relationship a fair amount. Okay? You're going to use this relationship a fair amount. So just to remind you, because you're going to have some exponential forms, I find that there's some easy tricks here, but this trick here you want to remember, because I find this as errors in when you start doing calculations. Note that if you have e to the a, e to the b, this is the same as, right? They're just exponents of powers, right? Very, very simple. But what people miss quite a bit here, okay? They miss quite a bit. So with that relationship right here, we can then go in and start looking. And this board is screwed. I think it's going to get darker and darker. Okay, here we go. So here's another thing here. We have to convert all rectangular coordinates into the polar form. That's our whole goal. Yes, sir.
The R equals to A squared plus B squared, so square root of C squared.
Yes, absolutely. I would agree. Thank you. So, okay, so here's things that, so there are a couple of things. So, a couple of relations that constantly show up. Okay, so these are the things you want to pay attention to. It turns out that, think about this here. So if I have e to the j of, let's say, pi over 2. So remember, these guys are in radians, by the way. Make sure your calculators are in radians. Okay? When you're doing spatial calculations, they got to be in radians. So what you'll find here is that this is the same as cosine of pi over 2 plus j sine of pi over 2. But we already know that this is 0. And sine is 1, so this is j. So in other words, when you see j in a circuit, you got to come in and you got to write this as j pi over 2, or in degrees, 90 degrees. Okay? Any j has to be converted into this polar form. The other one is this j to the pi, which we already know j to the pi will give me cosine of pi and sine of pi. Clearly this is 0. So here's the tricky one. -1. If you have a minus, you got to convert that into the phasor. So in other words, I gotta write this as J pi, which is the same as J 180 degrees here. Because you're gonna see that one of the things that we pay attention to a lot is going to be the phase. And I'll talk about the phase here in a minute here. So what we're gonna see here is that when we have, so by the way, that's the end of the review. Okay, so now I'm assuming that you're an expert at all of this. Okay, now that we're clear about this, let's move on here. So what we're going to do here is that we now will have some AC circuit, and we assume an exponential form has a solution. So imagine that we have a differential equation, right? We have some differential equation. And when we have some differential equation, we're essentially going to define a function z as a function of time. And when I do that, it's going to have some, I want to call that max, so it has an amplitude. And it has a function here that's going to be what? Omega t plus theta. So what you're seeing here is that the circuit is oscillating with some frequency omega. And there's this angle theta here. And what is theta? Well, theta is the angle of the complex vector over there. And what you're going to find here is that this is what happens in the circuit. So when you assume this solution, you're going to see that we're going to be able to separate this stuff. And the way we're going to separate this stuff is that I'm going to get some piece that looks like this. Okay? So you're going to see there's two pieces. What you're going to see in this first piece here is that you're going to get a changing amplitude and phase. But this term over here has, for a non-changing frequency, is always constant. So let me say this one more time. The way I'm going to solve my AC circuit is that I'm going to assume a solution. Now, if I'm only looking at a force response, that force response must depend on omega t. And when we do the calculation, you're going to see what changes here is the amplitude and this phase angle. Phase angle meaning the angle of the phasor. But what you're going to find here is that when I assume this solution, this guy will change, this guy will not change. So it's going to be on both sides of the equation. I'm going to have the exact same thing. So you know what's going to happen? This cancels out. So it becomes independent of frequency. And when it becomes independent of frequency, we call that the frequency domain. So when I look at my solution here, we're going to have this time domain, and then we're going to have a frequency domain. And so when I look at this thing here, I could have, right, this could be current or voltage, of course, right? That's what we've been calling XFT for some time. Yes.
How are you able to split those into two terms? The plus.
Yeah, that's time.
You know what? I'm going to have to agree with you. How about this thing right here? Yeah, that's thank you for the correction. You're absolutely right. I cannot split those two up together. So what you're going to find here is that when I do this time domain, I'm going to have what? I'm going to have some amplitude, and then I'm going to get cosine of omega t plus this phi here. No, I've been calling it theta, so I got to keep calling it theta. But in the complex plane, what we find here is that we define a complex vector like this. And this complex vector is really this guy right here. So this complex vector has what? It has some magnitude, and it has some phase here, like this. And what you're going to see here is that this is now simplified in notation, where they define this as xm with the phase angle of theta. So I can rewrite these any way we want to. And so what we're going to find here is that we're going to move between these two. So if you look at this thing here, we're going to do a calculation. So it goes something like this here. So we're going to start off with a time domain circuit. That means we have differential equations. And then what we do here is that then we map into complex plane. And then so now I have a frequency domain circuit. So that means that we now have phasors. So we calculate the circuit in phasor language, and then what we do here is that then we map back into time domain. So to sort of show you this flow chart, what do I mean by this flow chart? You're going to have some circuit. So you can imagine that I have some circuit that has maybe about a cosine omega t. And then I'm going to have some elements, whatever these elements are, in whatever form. And so what I do then is that I then go into, so then I make it into a phasor circuit. Okay, I make it into a phasor circuit. So now this cosine omega term is actually gone. So now everything's in exponential form. So that means here that you're going to see that if there's no phase, look at that, this says cosine omega, there's no phase. So the phase angle here would be 0, for example. And then what I do here is that now I have these components here. So components are now in phasors. They are now in phasors. And so that means here, this solution, so when you look at this solution should be something like, let's call this B cosine omega t plus phi plus theta. But now, I'm going to get a solution, and this solution is going to read like what? Well, it's going to be B be e to the j theta times e to the j omega t here. And you're going to see that the only thing we deal with is the phasor part of it. And then we get a solution. So now I have a solution. I should say a phasor solution. And with this phasor solution, I then go back to the time domain solution. And the way I do that is that now I have a phasor that looks like this. And then what I do now is the way I get back to this is what do? I take the real part of this thing. So now, if I take the real part of this guy here, I'm then going to take the real part of xm cosine of omega t plus theta plus j x of m sine omega t plus theta using the Euler relationship, and then I get a solution that then reads x of m cosine of omega t plus theta, where now I know what that amplitude is. Now I know what that phase angle is. And so I then get a solution for whatever voltage or current that we're actually calculating here. So that's how I'm able to move from the time domain circuit into the phasor domain circuit. Any questions? So this is the image that I want you to have in your head. So the image is, in our differential equation, we're going to assume the solution. When you assume the solution, you're going to see that the time part cancels out, and the only thing that's left is this guy. I then put it into my circuit. When I put it into my circuit, I then treat this as a linear circuit. I use mesh, node, VDR, series reduction, just like we did before. I get the solution, and then it's in phasor form. So now it's in phasor form. I then have this phasor form solution. I take the real part. When I take the real part, I then get the solution. Where now I know that amplitude, and I know that angle right there. So that's the whole process. So now I'm going to do what you already know, but the only trick that I got to do here is I got to show you how to write these components into phasor form. But we need to sort of like play with a little bit of language here before we get started. Because my understanding is that you guys really didn't spend very much time on like Eli the Iceman. Right? Yeah, my assumption is that you didn't, so let's talk about, we won't talk about Eli the Iceman yet, but what an actor. Okay, so now all I'm trying to do is just sort of like prep you, right? All I'm trying to do is prep you so that you have at least some understanding of why we do this. Okay? Why do we do this? Because it's a hell of a lot easier, that's why. Okay, the other way is complaint. It is totally insane to do it any other way. So what we want to do here is that it is customary to write all functions, you know what, I should say AC functions, into cosines, not sines. So sines cannot exist. So you have to convert everything into a cosine. So to give you a sense of what we do this, let's say that I have a vector, excuse me, not a vector, but I have a current that reads something like this. So I write 4 cosine omega t, and then I'll write 80 degrees. Okay? So if I want this in polar form, what I do then is that I take its magnitude of that vector, so that magnitude of this guy is 4, and then I only focus on the angle. So when I look at this angle, it's negative 80 degrees. So what do I call this? This is my phasor right here. Okay, that's my phasor vector. So if I was to plot this in the complex plane here, that's negative. So you can see here, if this is the real, then that means I would have a vector that looks something like this. This is 80 degrees, and the length of that is 4. Right? Nice and simple. Now, let's say here that I have a voltage, and this voltage is now 8 sine omega t minus 20 degrees. Well, I can't have a sine, so I got to convert that. So what I do then is I use that relationship of moving sine to cosine, and if you remember this, we find here that the sine of theta is also the sine, a cosine of theta minus 90 degrees. So when I look at this guy here, I'm going to convert this guy, so this guy now looks like what? So it's got to be 8 cosine of omega t, and then I got to add 90 to 20, so I get 110 degrees. So in this case here, my phasor in polar form would then read 8 at 110 degrees. That's what I mean that we got to convert everything into cosine. So if there's a problem where you get a sine, your first job is to add that thing. You add that 90 degrees. So what does this mean here? Well, one of the things that we see here is that when we start to look at angles, and we're starting to look at the difference between what do I mean by current with the phase, what do I mean by voltage with the phase. And so when I'm talking about the phase angle, I'm looking at this value right here. I'm looking at this value right there. And so by definition here, what we say here, so when I look at this definition here, is that if the current reaches its max value, in other words, the peak, before the voltage, then we say here that the current leads the voltage. And so what this means here is that, so if I start to look at this thing here, is it sort of something like this here. So if I look at this, what I'm seeing here is that I'm effectively looking at where's the peak values here. And so I'll exaggerate this thing here, but you can imagine that I have a value that goes something like this here. And let's say, for example, this is the current I here. And then, if I look at the voltage, where the voltage is somewhere like over here, should have made this smaller or bigger, but I didn't. What you're seeing here is that this angle right here, this lag between these two, right? I would call that the phase difference here. So this guy would be the phase difference between peaks. And then we would say that the current then leads the voltage by this value, d theta. And so, in this case here, you can see that the phase difference between these two must be what? 30 degrees, right? There's a phase difference between the two of 30 degrees. So when we start to calculate these things, what you're going to find here is that it's going to be important to interpret what that phase means. And that's where you get this loving expression called Eli the Iceman, which we'll get to here very quickly. So the first thing I want to do is I want to go over example 1. Right? I'm pretty sure I gave you the examples at the beginning of the semester. Is that correct? So now I'm going to look at example 10.1. And this is nothing but pure mathematics here. And what you find here is that you get a mathematical relationship here that reads 5 36.9 degrees times the quantity 10 minus 53.1 degrees divided by 4 plus J3 plus 6 minus J8. And the goal here is to put this into polar form. Okay. Our goal here is to put this into polar form. Okay. So here's where you learn to really love your calculator. I mean, like, really love your calculator. You could do this one of two ways here. If you have the 89 or something equivalent, you're looking really sweet. Because you could have mixed complex numbers in your calculator and just multiply this out. So you would just go, okay, put that into polar form, multiply this by polar form, divide this by this rectangular form. And then you get an answer. Now, for the less advantaged people, we should do it the other way, right? So mathematically, what are you actually doing? So remember, this is in complex form. We always want complex form. We always want complex form. So what do you want to do? I can add these right away, right? And then these guys, I have to convert into rectangular form. So if I look at this mathematically, how can I make this out? Well, I can write this as well. 5e to the j 36.9 times 10 e to the minus j 53.1 degrees. Okay, so that's the numerator. And if I continue with the numerator, check out what the numerator does. So now what am I going to do? I'm going to multiply 5 times 10, which is 50. And then, what happens when I have exponents when I multiply them? It's the same as adding them. So if I add these guys, okay, is that 16 or 17? It's like 16 something, right? Yeah, it's got to be negative 16. So it's got to be e to the negative 16. Is it 0.2? Okay. So note, look at that. So if I rewrite this guy, what does this look like? This is same as multiplying 5 times 10, and then adding these two, and that's what I get. So I could have done the exact same thing. So by working with these angles in this form, which is more customary than working with exponentials, it's the exact same process here. Now, let's focus on the other one. So if I focus on this other one, what do I do here? Well, first of all, I gotta convert this into polar form, so that means I gotta get what? So I'm gonna add these together. So I'm gonna 4 plus 6 is 10. 3 minus 8 gives me 5. So I then have 10 minus j, 5. And then what do I gotta do? I gotta put that into polar form. If I put this into polar form, what does it look like? Well, in this case here, to get this into polar form, I gotta take the magnitude of this, so it's gotta be what? 10 squared by 5 squared square root. So I get 10 squared, 5 squared, square root. And then I gotta find the angle. And the angle in polar form must be what? The y component, the imaginary component, divided by the real component or x component. So then it's got to be the tangent inverse of minus 5, 10. So I'm pretty sure I calculated that someplace. I got negative 27. So if I do these numbers here, I get 11 with an angle of negative 27 degrees here. So now, I just do the algebra now. So if I do the algebra, you can see that in the end here, I'm going to get a value that will be 4.54. And then I add these angles, right? So this angle, how do I add this angle? I take this guy. Remember, it's in exponential form. So I could just bring it up. Okay, I'm probably not doing this right. So check this out. So this is the same as this. Okay, this is the same as this. So if I have a power in the bottom, when I bring it up, it's going to be positive. So then this positive value tells you that it has to be 50 over 11. Now it's e to the minus j 16. Here, let me make, so this is minus, now this is positive. So this will be plus j, which will be 27 minus 16.2. And when I calculate that angle, I get an angle of positive 10.4 degrees. So then this would be that thing in solution formula. So can you get really fast at this? Yes. What would I probably do? Punch it into the calculator. And then I get this right away. I know you could do it on the 83. I think the 83 and the 84 actually act exactly the same way. It's when you get into the complex matrix form that the 83 and 84 make you work a lot harder. Okay, so that's essentially a Phasor calculation. So now, let's do it. So now what we want to do here is that we want to get into what is a Phasor circuit. Phasor circuits and RLC component. So we've already seen this in the lab. Okay? So this is an extension of the lab. Okay, so our job is to change this thing. So what I'm going to do here is that I'm going to do what I said before. I'm going to start with the regular circuit. That regular circuit, what do? I convert that into a Phasor circuit. In other words, into polar form. Once I get it into polar form, I solve that linear circuit, which will be frequency dependent, and then I can convert back into that. So what I want to do here is that I want to do this as easy as possible. So So if I was to sort of like talk about my process of thinking here, I would say step one here tells me what? So first I gotta convert circuit into a phasor circuit. Okay? And the way I do that, if I have an assumed solution, that solution I'm going to write as what? Z, which has some amplitude, e to the j theta times e to the j omega t. And I'm going to show you that this term always drops out. Always drops out. And then what I'm going to do then, in step 2 here, I'm going to solve the phasor circuit. And when I solve the phasor circuit, you're going to see that this amplitude is going to change, as well as the phase. Once I do that, then I go to step 3 here, and then I convert phasor solution back into time domain solution. Now note this convert back to the time domain, I'm only going to do that initially, but then I'm going to stop doing it. Because we don't need to do this. We'd rather stay in the phasor form and then interpret what the hell is going on. Okay, it's better to learn to see phasor instead of stick with that time domain solution. Okay, so let's deal with the simplest circuits. So the simplest circuits here are resistor, a single inductor, a single capacitor. Okay, so let's talk about a resistor circuit here. So the easiest resistive circuit I could possibly imagine here, I imagine that I have a source that looks like this here. So I have some source that has some amplitude, and it's cosine omega t. And I now have some resistive element R. So what we want to do with this circuit here is that we want to think in Ohm's law. And when I think about Ohm's law, what do I mean about Ohm's law? I mean in Ohm's law, I have a current and a resistor value like this. And ultimately, we could look at this one way or the other. But typically what they say here is that we should look at this in terms of I over V, but then that inverts the resistor part. Okay, so what we say here is that we could make this VR over IR, and that must be a resistive term with units of ohms. So no matter what happens when I talk about an inductor or a capacitor, if I set up voltage divided by the current, it must have units of ohms, period. And that's what I'm going to try to show you with the phasor circuit that exactly happens here. So this one seems a little bit silly here, but here we go. So what we do here is that now I got to go into a phasor circuit. So what I see about this phasor circuit, it looks like this. So that means here I replace my source with some amplitude, e to the j omega t. And my assumed solution for the current must also be the same form. So the the current must have the same form, right? Must have the same form. Why? Because this is the forced response, right? I'm forcing the circuit to behave in this language of cosine omega t. So that means that I of t in phasor form should be I m e to the j omega t. So here I go. So now what I have here is that then I apply Ohm's law. Ohm's law says that Vs must equal I times R. So if I plug this in, my assumed solution for the source must be what? Vm e to the j omega t. What's the current going to look like? It's going to look like Im e to the j omega t times R here, and look what happens. That term cancels out there. The j omega term always cancels out. So what does this say? So this implies here that Vm must be equal to Im times R. In other words, Vm over Im is equal to R, and this is what they call the resistive reactance. And remember, this depends on frequency. And so when you look at this relationship, focus on this guy. Does not depend on frequency. It's just a constant. So if I plot this guy, actually let me do this up here. So if I plot this guy, what we see here is that if I plot, which sometimes they call this the XR reactance, you can see that for all frequency, this has no dependence on frequency. So regardless what this frequency is, this guy's a constant. It never changes. So what this tells us here is that the voltage is in phase with the resistor. So if I was to plot these curves, remember these guys are sinusoidal here. So if I have a curve that looks like this here, and this is the voltage as a function of time, the current will also be in phase. And so this would be I of t. And so what we say then, now note this is kind of funny, right? Because I'm plotting two different units simultaneously, which is not valid, but you know what I'm going to say, right? We're among friends, so we don't care about that. So what we say then is that the current is in phase with the voltage. Okay? So that means here, if in the complex plane now, in the complex plane, you can see that it always has an angle. So you can see that when theta is equal to 0 degrees, then we say it's resistive. So now let's talk about the inductor circuit. So the inductor circuit, I'm going to write exactly like I did before. But this time I have an inductor. So now you'll see that this reasoning really, shows exactly what we've been talking about and what I've been trying to get you to think about. So I'm going to do the exact same thing. So what am I going to do? I'm going to go to a Phasor circuit. Okay? I'm going to go to a Phasor circuit. So that means, here I go. So now I'm going to go to a phasor. So that means ds equals dm e to the j omega t. I becomes in e to the j omega t, and then I do the exact same thing. Okay? So now I apply Ohm's law. So what do I mean Ohm's law? Well, that voltage and that voltage has to be the same. Now remember, this is a bit tricky doing that, but I don't care. So then what we say here is that the voltage of the source must be equal to the voltage of the inductor in the Phasor circuit. So now let's write it out. What does the source look like? Check this out. So the source has to look like this here. Right? That's what the source is. Now, what about the inductor? The inductor is what? Right? It's got to be that. Now, look. I have a derivative term here now. A derivative means that I got to bring down the j and the omega. So if I do that, I'm going to get what? I bring this guy down. Am I being, so how about if I do it like this? Just to make sure everybody's seeing this. Right? I get that. So when I take that derivative, I'm going to get what? Im e to the j omega t times j omega L. What did I tell you about these guys here? Look at the omega t terms. What are they doing? See how they always cancel out? Essentially, we could start ignoring these terms, as you'll find out here. So what you're seeing here is that now we want what? Ohm's law thinking. Right? So now we're saying we want Ohm's law thinking. Ohm's law of thinking says that if I have dm over Im, it's equal to what? J omega L. So right away, this tells us here that this is what? Resistive. And what we do here is that we define this as XL, and we call this the inductive reactance. So that means when I take the units of XL, they must have units of ohms. It's a resistive term. So what you're seeing here is something like this here. This means that a circuit, when we talk about an inductive reactance, what this means here is that if I was to sort of like think about it, right? So if I was to make just some quick remarks here, before we leave here, is that we have this inductive reactance. So this means here is that the inductor acts resistive in AC circuits. And that's not such a huge surprise here, because we find it like this. So if I have low frequencies, that means omega is small. That implies that I'm changing the frequency very slowly. So therefore, the back EMF of the inductor is not large. But if I go to high frequencies, then, so here, I would say it acts short-like. But at high frequencies, the back EMF is huge, right? Because you could imagine here, if it's dependent upon this change in time, if I change it very, very, very quickly, as we've been talking about for some time now, the inductor voltage gets way huge. And it could stop the current dead in its tracks. So then, it acts open like. Right? If I have high frequencies, it's got to do that. And we saw this in the lab. So when we plotted these guys here, right, in the complex plane, oops, not in the complex plane, but this as a function of omega, we saw in lab that you were getting some term like this, right? This is what we mean by acting like a short. This is what it means by acting like this way. So what you're seeing here is that you're seeing something like this. If I plot this in complex plane, what do I see here? Well, I see that this vector, right, this vector right here, XL, is J omega L. In which direction does it have to point? It has to point up this way. And you could see that XL in this complex plane right here, what you're finding here is that if it's small, that must mean I have low omega. If it's large, then this implies here that I have high omega. And you're seeing that this vector component gets very, 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 very large here. I gotta stop, because I gotta jump into the next piece. So, okay, remind me, when are we meeting again? Is it Tuesday? Tuesday, 2 o'clock, right? You know what, if you want me to show up, some of you may want to email me. Because I got too much on my plate right now, and I'm gonna forget. Okay? So, Tuesday at 2 o'clock.